What's up guys, my name is Achana. Welcome back to my code review series, the series in which I take a look at all the various code and projects you sent me. Right. I don't know why I do that. Right. So first of all, we're in the new office. Might still be a little bit echoey in here, so it'll take a while to settle in. I won't give you a tour just yet because I'm still like basically building parts of it. I've pretty much optimized this camera angle just to show the good parts. So the stuff that's off camera, Anyway, for the longest time now, we have been looking at the 2000 hour game engine. Someone made a game engine, spent 2,000 hours on it, and well, I had some thoughts on it. So the previous video, I'll have it linked up there, but really, like the previous 5 code reviews have been all about that. But today, since we are here in the new office, I thought it would be only fitting to look at a new project. And so I found this email, Path Tracer project review request, and the screenshots look pretty good. So I haven't taken a look at this yet, but I'll explain why I chose it. First of all, you guys have been begging for the ray tracing series to return, and I know, I'm sorry, I've just been going through a lot in life at the moment, and I don't have time to sit down and give that series the attention it deserves. So I promise that next year, things are gonna happen. The other reason is that I don't think we've done a path tracer in this code review series yet. I know we've done ray tracing, or ray traces that people have submitted, but from memory, that was a while ago. From memory, that was like the ray tracing in a weekend kind of thing. Like it was fairly small scale, whereas this looks like path tracing, and it's done in OpenGL. So I expect this is on the GPU and architected a bit differently, so hopefully we can dig into that. I mean, I haven't taken a look at this yet, but this might be a multi-episode thing as well. So let's have a read of this email. Hi Chono, my name is Edward. I'm a 15-year-old programmer from Ukraine. I've made a path tracer in C++ using OpenGL that I've been working on for about 5 months. Right, so that's 3,650 hours. Here is a link to the repository. We'll obviously take a look at that in a minute. The project contains a Visual Studio solution file to keep everything nice and simple, so everything should just work. This is what the 2,000 hour game engine was like. So I'm getting a little bit of PTSD, but aside from that, I have made a video on why that's probably not how you want to set things up. I'll have it linked up there. The proper way to set up C++ projects, obviously it's subjective, it's my opinion, but that is the video to watch. And I would recommend if you are just making Visual Studio solution files, project files, committing them to GitHub repositories, you might want to take a look at that to see if that might suit you better. Features. So we've got 3 different types of objects, cube, sphere, and plane. Okay, so I expect this does not just support arbitrary meshes made from triangles, which is not, you know, terrible. I mean, 15 years old, 5 months. So let's just keep that in mind. 3 different materials. So we've got light sources, emissive materials. Okay, so we can have materials themselves be light sources by being emissive. We got rough and metallic and lens. Lens, I'm expecting maybe they mean like glass or something. Like something like this would be lens maybe. Depth of field effect. I like how the letters are bold, just so that we know that's DOF, guys. You can load any image you want for the skybox, PNG or HDR. Okay, cool. I'm expecting that has to be like an equirectangular or a cube map or something. I guess we'll see. We've got some controls, WASD, space, and left shift. Move the camera, mouse, rotate the camera. How to show you why, make a screenshot, cool. Feedback I'm looking for, optimizations, code structure. Okay, cool. I like talking about that stuff. Thank you for reading my email. Hopefully you will get a chance to review my code. Best wishes, Edward. P.S. I don't have much experience in C++. I learn it mostly off of YouTube and your videos. And that I think is supposed to be like a smiley face because people from that region tend to just add like right closing parentheses to mean like kind of like smiley faces instead of writing like the colon and the whole thing. So I don't think that's a mismatched parenthesis. All right, so here is the GitHub repository. We've got some libraries with a Y, beautiful, love to see that. So yeah, I mean, this looks pretty good. I'm kind of excited to take a look at this actually, because it does look really good. It seems to be OpenGL. There's a bunch of useful stuff here. I'll obviously have the link to this repository in the description below if you guys want to take a look at it as well. Now, I just want to stress, if this does look cool to you, and you want to learn the math that goes behind something like this, because believe me, it's basically purely built off of math. You can take a look at my ray tracing series if you like. If you have some extra time this holiday season, then it's a really good opportunity to get stuck into this stuff with the sponsor of this video, Brilliant.org. Now, Brilliant.org is an amazing website filled with lots and lots of really high quality courses on various STEM topics. The math that goes into ray tracing, it's there. You can learn like all of it there. Even if you're an absolute beginner, you can start with their everyday math course. But then as you get better, you can move on to algebra, linear algebra, calculus, and that will really teach you pretty much everything you need to know. But why learn it on Brilliant? The reason why I love Brilliant for this kind of thing is because all of their courses are extremely engaging and interactive. They're super visual. Like take a look at this calculus course, for example. Look at how you can move these sliders to manipulate the numbers and visually see what's going on. That kind of connection with the math, I think is really, really important if you want to learn it well and quickly. But then it's not just playing around with these sliders. Brilliant will also quiz you to make sure that you're actually learning and retaining this information. And as I mentioned, you can get started completely for free. Brilliant have a 30-day free trial that you can use to investigate all of the stuff that's on their platform and see if you like it. And if you do go on to like it, they've also been nice enough to offer the first 200 subscribers 20% off an annual membership. So go ahead and be productive this holiday season. 30 days is plenty of time. Just go to brilliant.org/thecherno, check it out for yourselves. Huge thank you to brilliant.org, as always, for sponsoring this video. We got some scenes here. Anyway, I'm just gonna clone this. We're gonna take a look at it locally. That makes more sense. Okay, so I've checked it out locally. This is what we have. A solution file as promised, executable, OpenGL.exe. It's a little bit scary. Got a bunch of shaders here. I wouldn't personally commit executables. If you do want to make your project just a little bit easier to access for people so they don't have to build it themselves, I would make a GitHub release instead. I don't actually know if there were any GitHub releases here. No. So you can make a release instead of doing this, and you can actually upload built binaries. Now, opening up the solution file, this is what we're created with. Let's just go ahead and try and build it in release. Okay, we're getting a bunch of errors. So the should work, should in bold, is not, it's failing us here. So cannot open includes. There's just the Visual Studio project file. So let's take a look at the includes. So we've got release. Okay. So include directories. This is an absolute path, right? Okay. So whenever you're setting include directories and library directories, and let's have a quick look at the linker. So that's just linking these libraries, and then we have the library directories, setting up the directories for them. Whenever you are setting up any kind of path inside your project files, whether that be in like a build system like Premake or just directly in Visual Studio project files like this, do not ever use absolute paths, because obviously absolute paths are only going to be relevant to your environment, to your computer, and in this case, obviously, to your username. There are lots and lots of ways to avoid this and just do this differently. And by the way, my video on how to properly set up C++ projects, which is linked up there, does go through how to set this up using Premake, and you won't have this problem. But specifically for this environment, since we are dealing directly with Visual Studio project files, the way that I would set this up to fix this is probably just by using the macros that Visual Studio provides. So instead of us going into here to get to this libraries with a Y directory, by the way, just quickly, because I know you're Ukrainian, you're 15, you might not know English that well, libraries is spelt with an I, but we'll leave it like this. So to get to this directory, you have basically two macros you could use, solution directory or project directory. And so that will give us this basically. If you're not sure what the macros are, there's this macros tab over here, or this button rather, you can click on it. You can type in, for example, project directory, and you can see it is this, right? So that is the directory of that project file. This over here, this VCX file, that is this project that we see up here. And this is the directory it's located in. There's also the solution directory, for example, and that is the directory of this solution file. So you can use either one. I'd probably use the project directory. So I would generally just write something like $, and then in brackets, in parentheses, project directory. Now, if you take a look at macros, you'll also see that project directory ends in a slash. So here's project directory, it ends in a backslash. So that's why I'm not putting a backslash here. I'm just writing project directory and then directly libraries include. So let's, I guess we'll copy this because we also need to make sure that we do this for here. So I'm gonna go ahead and add that in. So now if we hit OK, oh, by the way, I was only editing the release, unfortunately. So just make sure that you make this happen for all of them. Okay, great. So let's try building again. No include errors here, and it seems to have worked. Let's go ahead and run this, see what happens. Okay, so it's not quite working for me. It's coming up on this monitor, and every time I try and make it active, it just flashes. You can probably see my screen flashing, actually. So I think it's like trying to start either in full screen or something. Let's go ahead and fix this. So what is it doing? So GLAD. Oh, we're using GLAD here. Okay, width and height, 1920 1080. Okay, that doesn't seem like full screen unless it's being set to full screen. Yeah, I mean, it shouldn't be though, because it's null. Oh, that's shared. Oh, right. Sorry, yeah. So let's go ahead and not make it full screen. Because full screen, for some reason, wasn't working, but also I've flipped my main monitor for the purposes of recording this, so Yes. Okay, here we go. This is what we see. Viewport doesn't resize, unfortunately, but this is it. I can't stop moving the mouse, and also I guess I have to add an object, submit. I have to write something, ASD, sphere, here it is. I think there are some scenes we can load. Load a scene, many spheres. Oof, all right, many spheres too. Close, oh, close. I thought close was the name of a scene. Why is this not working? Path tracing settings. Oh, right, you have to switch. This is, I think, the rasterized view. If we go back to the repository quickly, because I think there was some stuff here. So R, disable or enable the render mode. So we have to press R. Hey, there it is. Awesome. Okay, so this does seem quite, whoa. Why is it getting so bright suddenly? It started off dim and then it just kind of went bright. That doesn't look right. Yeah, it looks really nice though. I'm a little bit sus about the brightening / warmer tones that seem to be coming out later. I don't know if there's any tone mapping going on. And just if we take a look at, if we dissect this a little bit, like this is very hot versus this, you know? So that's why I'm thinking maybe this is HDR, but it's not being appropriately tone mapped potentially, because this is also very, very bright. I don't know if there's a light source here. There's no light source. It's just the HDR image, like the backdrop itself is acting as the light source, which also could be part of the problem, because depending on what the HDR values of this image are, this could be like, you know, 200 or something. And if it's like super bright or 2000 or whatever, then that can overwhelm the image. So sometimes like what we do in Hazel is we actually clip the upper values of super bright HDR, like skyboxes basically, or environment maps, I should probably call them, because sometimes they can be so bright that they just ruin your scene. But I don't know, maybe we should open this up in RenderDoc and see what the actual values are, because they're hard to see. It's also weird that it just kind of gets brighter and brighter over time like this. Like that, I don't think that should happen. It almost seems like the accumulation is being a little bit more additive than it should be. But anyway, either way, this looks really cool. I'm really excited to dive in and take a look at the architecture behind it, because it does seem like it's running fairly quick. Like, it's not the fastest that I've ever seen, but you know, it does seem like, okay, the camera just stopped moving. Why did the camera just stop moving? I don't know, the camera just stopped moving. But it does seem like it's running quicker than just kind of CPU-based ray tracer or path tracer would. So I expect this is in fact done on the GPU. So that's going to be super interesting to dive in and take a look at. All right, so the main file, the main function over here. My advice always is this should be clean. This should be as clean as possible. I know people have been asking for this for a while, and I think it's finally time. I think it would be a good idea for me to make like an application / game engine architecture series. Kind of like what I did with how to properly set up your projects in C++, kind of like that, but for just general applications and game engines and games and all of that. Because this is a common thing that I see in almost every project that is sent to me, and it would be nice to just have a resource to point towards. What I will say though is that again, this person is 15. And I don't know what experience they have. I don't know what their background is. I don't know if they're studying this or if this is just like self-taught. So I'm not being harsh. I'm not trying to be harsh or anything. But of course, there are certain things here that stand out to me as being, you know, something that a non-experienced person would do. And also I feel like a lot of you people watching my channel, whether it be you're watching these code reviews purely for entertainment, which is fine, but if you're watching them to learn, then a lot of you are probably in a similar position where you don't have a lot of real world experience. Just because I don't imagine professional engineers watching this content for anything other than just entertainment while eating lunch or something like that. Correct me if I'm wrong though. So as a starting point, I definitely would take these things and just segregate them out into like a window class, into an application class. I would have like an application lifecycle and window events and all of that really well defined, because that's like the heart of your entire program. Having things like, you know, shader uniforms being set right over here inside the main function is also a little bit weird. It's like the main render loop is actually in here, and all of the draw passes as well. Like you know, all of this is like a draw call here. We've got some post-processing going on. We've got the swap buffers and the poll events and all the key stuff. It's all just done inside this while loop inside the main function. Now, at a pro of this, the good side to this is that it's easy for me to code review because I don't have to dig through files. So that's kind of nice. But in general, you know, this should be architected differently. And the main reason I think for that, aside from the fact that this is just going to end up growing and it's going to be harder to manage, is the fact that as software tends to grow and branch out to potentially different platforms and different render APIs and whatever it might be, this architecture becomes unfeasible. It's not even about code, like how clean is your code and how easy it is to maintain, how easy it is for people to go in and adjust it if they've never done it before. It's not even about that. It's about like what is physically possible and what is not, which I realize is not that applicable to this project, but that's why you tend to see, professional software architected differently. It's because the requirements end up obviously being at a much larger scale, and things like this just simply do not work like at all whatsoever. Now let's go up. I don't want to talk too much more about architecture because I've talked about it a lot in my previous code reviews. I'll have a link to the playlist in the description below. You can just watch all the code reviews and you'll probably learn quite a bit of what I would say otherwise. I wonder if someone could make a brand new code review by patching together bits and pieces from all the different code reviews, and that's literally what I say because I tend to repeat myself quite a lot. But I want to talk about some of the more interesting things today. Like OpenGL. And how is OpenGL used here? How are the draw commands happening? How are the shaders running? How's the ray tracing happening? I feel like that might be a little bit more interesting than just standard C++ code architecture stuff. So the first thing I want to point out is that this, what we're doing here is we're setting up the OpenGL core profile to be 3.3. This is quite old. So OpenGL 3.3 released 11th of March 2010. So step one, do not use OpenGL 3.3. It's really, really old. I'm glad to see that the core profile is being used here because there's also the compatibility profile. That lets you use deprecated legacy things that you shouldn't, and it won't be like, no, that's an error. So at least the core profile is being used. However, I would not be using this. I'd be using 4.5, 4.6, something like that. To be real, I wouldn't be using OpenGL in the first place. I'd probably be using Vulkan. But again, this is a 15-year-old person. This is someone who, Vulkan is very, very heavy. It's very difficult to learn for someone who has zero experience. So OpenGL's fine to use. There's nothing wrong with using OpenGL for something like this. I will say the only possible limitation I would see that is a real limitation is the fact that if you would like to take this and then move it to actually use ray tracing cores inside your GPU. And for that, you'd have to use ray tracing shaders, the ray tracing pipeline. That's not available in OpenGL. You need to use Vulkan or DirectX 12 for that. So, or I guess Metal, and there's other APIs as well. But my point is you can't use OpenGL for that. You have to switch to Vulkan. So that is a possible extension of this. Because if you're doing any kind of ray tracing these days, I think, the end game should pretty much always be, I want this to run on my RTX cores or on the ray tracing cores on an AMD card, whatever they're called, because that opens up an entirely new generation of performance that you definitely want to take advantage of. And as a bonus, on newer drive, the compatibility is a little bit it's not going to be as good as just standard. I think this is just using graphics shaders, to be honest. I think this is just using the normal graphics pipeline. I don't think it's using compute. We haven't taken a look at how the ray tracing happens yet, but we'll get to that. But my point was that ray tracing shaders might not have as much compatibility as compute in terms of drivers and support. But what tends to happen is on GPUs that do not physically have RTX cores, like a 1080 for example, the NVIDIA driver will actually fall back the ray tracing shaders to just run on compute. So there is an emulation layer, if you want to call it that makes that compatible. So that's why I generally advise people to use ray tracing shaders and the newer ray tracing pipelines if they're making things like that and they don't need to fall back past the 10 series NVIDIA GPUs as an example. Now, aside from that, we obviously create the window. Now we're using, it looks like we're using GLAD here. I don't know why we're using GLAD here. So I would not use GLAD. GLAD is actually an entire, I think GLAD is more than, wait. GLAD. No. GLAD is good. What am I confusing GLAD with? I was confusing GLAD with something else. Oh, GLUT. G-L-U-T. Okay, no, GLAD is fine. GLAD is kind of like Glue, G-L-E-W as well. OpenGL Extension Wrangler, that's the older one. GLAD, I think, is what people use these days. Man, it has been a while since I did any OpenGL. But yes, so GLAD is this. You can basically pick OpenGL, your core profile, 3.3 or whatever. Again, I'd go with 4.6. Probably core. So that's not too bad. That's 2017. So pretty much like most drivers past that date will have support for it. It doesn't mean your GPU has to be newer than this. It means your driver has to be newer than this. That's an important distinction. Anyway, you pick that, it gives you like a header file that loads everything, because with OpenGL, if you have any extensions that aren't core, Windows, for example, does not provide header files for that. So what you tend to do is you basically open up the DLL and get function pointers to certain extensions, certain functions that are within that newer OpenGL standard, so that you can call those newer functions. An example of a newer function that might be, not core in OpenGL like 1 are things like, I don't know if frame buffers were, but things like draw arrays definitely were not. So this, you can see, is coming in as a function pointer. Here it is over here. Here's like the signature for it. And it's going to be loaded as a function pointer when GLAD starts up. So that's what GLAD is used for, which is fine. We set the viewport straight away. I think, we did see a problem where when the window resized, the viewport didn't. One of the reasons for that is I don't think I would set the viewport as early as this, because what the viewport is for OpenGL is it basically tells you what portion of the frame buffer you can render to. So if you make the viewport too small, then even if your window is bigger and your frame buffer is bigger, you won't draw anything outside of that region, whatever region you set here, because it will be clipped. So in my opinion, this shouldn't really be here, because we might not know the final finished size of our window. Like, sure, we've requested this size, but what if my screen resolution is less? What if I'm on a laptop that's like, 1280 by 800 or something? Then obviously I'm not going to be able to get this resolution, at least not like physically on my display. If it's off screen, then obviously it doesn't matter. But if I'm not going to be able to get that, and also what if I maximize my window? What if I restore a previously run like resolution? Like, it's a bit early to just assume that you're going to get this exact viewport size here. Not to mention that because IMGUI is being used, I don't think IMGUI is being used for a viewport, meaning that there's an actual viewport panel, and that viewport panel will just contain like the frame buffer image basically being displayed there, in which case you obviously have to make sure that you're rendering the size of that IMGUI panel, not your entire application window. But I don't think that's what's going on anyway. I think that it's just rendering to the full window, and the IMGUI windows are being like, the IMGUI panels are being composited on top anyway. Okay, so we've got print OpenGL info, just prints a bunch of stuff here. Then we got create shaders. Now, when you're creating objects on the stack like that, you don't need to do this assignment thing. You can just do that. So I would probably prefer to use this. I don't think there's a difference in this case if you do that. Obviously, if you had it on multiple lines, then you'd be creating a default constructor version of this object and then recreating it with, a specific constructor. So like, for example, if you did like that, but you can see there is no default constructor anyway, so that's not going to fly. But I guess it just saves a little bit of space if you write it like that. Then we got some other stuff over here. We got the camera. We got this rect VAO. So I'm assuming this is a vertex array object that makes up like the rectangle. So yeah, I forgot OpenGL, you have to have vertex arrays as well as vertex buffers. Very annoying, but that's the way that they choose to kind of lay out all the buffers. Okay, then we got a camera. So we got some stuff here. Yeah, just using trigonometry, that's fine. I mean, I probably would use quaternions, but I realize that's probably next level for a 15-year-old. I certainly was not using quaternions at 15, so it's fine. You can just use trig, that's okay. Then we got random number generator, just using the normal kind of built-in one in C. Not the best random number generator, especially, to use in a ray tracer. I have a video where I talk about how to write a random number generator in 3 lines of code. I suspect that this is not what's being used for... actually, maybe these are being pre-generated or something. Update random seeds. Okay. Whoa. Okay. Yeah, okay. So we're doing that, and then these, yeah, they make it to the shader. Okay, because I was going to say that maybe this is being used for like CPU side random stuff, whereas obviously we know the ray tracing takes place in shaders, so it will be different anyway. But no, this looks like this array of random values. Actually, it's not an array because these are seeds. So what happens actually? Let's investigate this. So update random update random seeds, and we regenerate them. There's 3 of them for all these, and then they wind up in the shader, and we update them every frame. Yes, I'm assuming this is like a base random number, maybe that's being used, in the shader, but it's just a seed still. So we can look at the shader. Where are the shaders actually? I don't think I've found them yet. No, here they are. So what is this default shader, for example? What default shader is default? Okay, that makes sense. So if we look at these random numbers, like, where are they being used? Okay, so yeah, so we are actually using them as part of a hash. So the random numbers are actually kind of being created on the GPU. It's just that we have a seed being set from the CPU. And then this also seems like, I haven't even, Tau step. I don't think I've even heard of that. But this, either way, this seems like a lot of work to get a random number. Because I have a video, as I mentioned, talking about how to do that in like 3 lines of code. So, so I would probably, I'd probably take a look at that. Again, quality of random numbers, especially when you're doing things like picking new ray directions and ray tracing related things. There's a lot of papers talking about different random numbers that might be better quality or might converge faster on what you want, importance sampling, stuff like that. So I'm not saying that this is wrong. I'm just saying that I don't know if maybe this person just doesn't know that there's like a nicer, easier way to do this, or they've specifically picked this because it works really well for their purposes. I don't know. I'm just saying that there is an easier way, in my opinion, that also doesn't involve you having to seed stuff. From the CPU, because that's also not great, having to set uniforms and update uniforms every frame, and also run this every frame to update random seeds if you just simply don't need to do that. Now, I will say that the other thing that I'm seeing here, obviously, is a lot of uniforms and no uniform buffers. This should all just be inside a uniform buffer. The biggest advantage there really is that all of this, like, look at what's going on here. This is a fair bit of code to run every single frame that will, first of all, update every uniform individually. I mean, I'm not sure if the driver will buffer it up and then send it in one go, whatever on earth the optimizations the driver might do. That's a black box as far as I'm concerned. It's annoying because you also have strings here that you then have to, you're doing get uniform location by string. That string has to be matched with shader reflection data and all of that to actually find, what variable you're trying to set, again, by name. What I would do instead is I would just create a uniform buffer, which contains all of this, and then you just, it wouldn't contain, samplers, because you can't put them in there, they're textures, but it would contain all of these just raw values, and then you could basically have a C++ side struct that allows you to set all of them normally as you would, and then you just kind of upload that and set that buffer into the GPU in one go, just before you draw, and that would be it. And then you can edit it as many times as you want on the CPU, because it's all inside just a buffer. If you have different sections here, or like different, for example, camera versus like random stuff versus just like, focus distance and maybe some, DOF parameters, you can obviously create multiple uniform buffers if you want. But generally, all of this stuff would I'd probably just shove it into one uniform buffer and then just set that once per frame. And then the benefit there as well is there's no names, there's nothing like that. It's just serialized. It's like just a byte stream of data that you're just uploading to the GPU. That's it. And it certainly does not need to be done individually, line by line, like this, to set all of these variables, because that can't be very efficient. If we scroll up a little bit though, because we're getting a little bit ahead of ourselves. We were talking about random. So then we got some key, again, this stuff is so not relevant to this part. It just creates so much noise that it's nicer to split it up into different files, different classes, stuff like that. Okay, we're creating a skybox, which is just a width and height. And then, okay, so are we then, because we're not loading it from file directly. Oh, we are, okay. So that's just an HDR image. Because I'm just wondering, like, if this is like a cube map, or how does this, because it looks like a 2D texture. So it could just be like the easiest way, obviously, is just to take a look at the file on disk. Okay, so I've just opened one of these in Photoshop. You can see it's an equirectangular image. So I don't think it's, this is typically not gonna probably go through the same pipeline as it would if you had a rasterized renderer, where you'd probably want to convert that from an equirectangular into, what is going on? I'm getting all these notifications. Sorry, going from an equirectangular image into a cube map, because that means that it's just faster to sample, and obviously you want to optimize for speed here. Ray tracers, path tracers, they're not as real time. I mean, they're getting to be pretty fast, and I would still say yes, you want to optimize it, but it's definitely not as crucial. And so that's why, the other biggest difference I would say is that when you are loading an equirectangular image as a skybox, as your environment map in Hazel, for example, the other big difference is in the rasterized pipeline, we will take that cube map and we'll filter it across the MIPS to blur it like a lot. And we'll do that in a very high quality, slow way. And the reason why is because that blur, that blurred cube map is then going to be used as the specular inside the PBR rendering code, because it's a way for us to just make, well, image-based lighting, but also just kind of reflections of the environment map work for rougher materials that wouldn't have a perfect mirror-like reflection. That is not necessary here, because when we're path tracing, when we're doing all that stuff, we're actually doing that by sending out a bunch of rays from that one spot that we hit in order to get those accurate, or rather not accurate, blurry specular reflections for rougher materials. So we're doing that like for reals, you know, but in rasterized, we're not doing that usually for actual objects in the scene. We're just doing that for the environment lighting. So because it goes through that pipeline and we want to have that blur, you generally have to do some processing to your environment map anyway. So it's not just the equirectangular into cube map conversion, it's also the whole kind of MIP filtering chain situation. We're not doing that here, so you know, doing this is completely fine. Obviously makes it easier. You don't have to like pre-process your environment map. You can just load it in as a 2D image and then just sample it using the equirectangular conversion to whatever you want. You know, when a ray goes off and misses, and then you want to sample from the environment map. Okay, we've got some textures here. So we've got two textures. I'm assuming it looks like we're kind of ping-ponging between the two. So the render API that he's got here as well is that textures get created and then used as the backing for a frame buffer. And then we've got Bloom and post-process as well. Now, this frame buffer has, I guess, two attachments. So we've got two color attachments, texture and Bloom texture. So it looks like, you know, the Bloom stuff, I guess only so if we take a look at even, I guess, default.frag, you can see we've got two outputs. We've got frag color and Bloom color. So that's corresponding to this and this, respectively. So Bloom color, I'm guessing, is just going to contain stuff that's bright. Yeah, and we're doing that by just seeing we're doing the dot with this versus Bloom weights that we're using, some kind of threshold, and if that's above 1, then we've determined that that color is bright, that light is bright, and it should be bloomed, so we set Bloom color to frag color, otherwise it just gets set to 0. Not bad. You know, I wouldn't do this because Bloom is, you know, Bloom is a subject. I have a video just called Bloom. You can go and watch that. And that, you know, I'm assuming this person has not done Bloom like I did Bloom. And no, it just looks like just normal Gaussian blur or something like that. And it's, you know, you can see it's split up horizontal and vertical passes. So this is, I think, just the learn OpenGL blur or something like that. But either way, you know, proper blur is done over like 10 or so passes probably, and it's downsampled, upsampled, blended together, you know, blurred using like tent filtering and stuff like that. Like it's a box filtering, tent filtering. Like there's a bunch of stuff involved. And unfortunately, well, I don't know if this is necessarily unfortunate, but if you want high quality Bloom, you have to do this. And typically this kind of filtering, this like pre-filtering as it's called, to separate the Bloom stuff, that would be done in compute later, and you don't necessarily need to worry about that, because if you have an HDR buffer, obviously this stuff is itself in frag color. You don't have to do this in your main draw pass, because you can do this later since the information is still contained, you know, within frag color. Because you can see the only input here at all is frag color. I mean, obviously we have threshold, intensity, and Bloom weights, but they're obviously related to Bloom. They're kind of Bloom parameters, as you can see here, that are actually constants. What's threshold intensity? That's a uniform, right? So the only input here that is calculated here is the frag color, which is also written out to the texture attachment. So my point is, you don't have to do that here if you don't want to. But also it's fine if you're just doing this kind of rough Bloom. It's fine to do it there. So that's why we got two attachments here. And then, yeah, I guess we're ping-ponging between the two. So we have like current frame buffer, for example. We're going through this and we're going to bind one of them as our render target. Then we make the default shader active, which is probably just going to do use program. Yep. And then we're setting all of our uniforms. And then this is Bloom. So yeah, generally we just have the bind vertex array, which is our rectangle. We just have a full screen rectangle. You can also use a triangle if you want, but I guess we're using a rectangle here, judging by the name. We're binding the skybox as texture 1, texture 0, and the current texture as texture 1. Current texture is one of the two textures. I thought this was used for, I thought this was, is this? Yeah, okay, right. So that's the opposite frame buffer. So that's what's happening. So you can see that these two things are, this is identical, this part, as you can see, but here it's 2 and 1, and here it's 1 and 2, right? So what's happening here is it's the opposite. We're rendering to one frame buffer, but binding the other one as an input. So If 2 is an output, 1 is an input. If 2 is an input, 1 is the output. I should have said that the same way. 1 output equals 2 input, and 2 output equals 1 input. So that's what's happening. So we're taking in each other, kind of, and that's why we have to do the ping ponging, because I guess it's progressive in some way. Usually you would have just an accumulation buffer and your final image buffer. But I guess you could do it this way as well, although maybe that's part of the reason why we're seeing that weird brightening towards the end, because something is maybe not quite right if you do it this way. But yeah, the actual draw we're seeing over here, because draw arrays will just draw those 6 indices, as you can see. We don't need an index buffer if you're doing this. I mean, you'd have to redefine the vertices. So if we take a look at rect VAO, then you can see that we've got 6 vertices, and some of them will be redefined. So like this left top is also here, left top. You can avoid that by using an index buffer, but it's not really a big deal. If you're just drawing a rectangle, but neither is drawing a rectangle this way. You could not do this. You could use a compute shader. You could define the vertices inside a vertex shader and just issue a draw command with 6, and that way you wouldn't even need a vertex buffer. So there's so many different ways you could do this. Honestly, it's almost not worth talking about it unless you're interested in me talking about it. But that's basically where the main pass happens, and then we move on to post-processing. I think I'm going to end this video here because it's getting long. I think I was correct with my suspicion that this will become a multi-episode series, taking a look at this project. So far, I like it. I think it's a really good subject matter. I think it's really good to talk about. There's a lot of stuff we can unpack here and suggestions we can give, as to how we would improve this code. It's making me kind of excited to get back into the ray tracing series and actually add path tracing to Hazel as well, because that's kind of half done. But I hope you guys enjoyed this video. If you did, please don't forget to hit the like button. If you notice anything here that you'd like me to expand on, let me know. If you like how deep I'm going into all of these OpenGL and rendering things, and you want to hear more of that, let me know as well in the comment section below. Don't forget to check out brilliant.org/thecherno. I hope you guys have an amazing Christmas and New Year, holiday season, all of that. And I will see you guys, I think probably next year. Goodbye.